Okay, so we left off talking about this idea that we're going to start talking about solutions to systems of linear equations. So if we write that in matrix terms, we're trying to solve this problem, ax equals b, and we're trying to find x. So mathematically, you can just write, well, okay, if a is invertible, that's just a inverse b. Maybe not too much more to say to the story. But if we're thinking about actually doing this computationally on a computer, it's a very different story, and there's a lot more details that is what we're going to be talking about. So what I thought I would do is lay out a bit of an overview of sort of what are the decompositions that we focus on in statistics, and we're going to talk about these in some differing levels of detail. So this is from a table in the Gentle book that's on the syllabus. So basically, I've laid out sort of some of the ones that we tend to work with a lot in statistical context. So the SVD comes up a lot in various algorithms, including machine learning, for things like topic modeling and things like that. The LU tends to come up in doing terms of solving systems of equations like that and doing inverses and matrices. The QR comes up because this is what the primary method that's used for actually doing regression and calculating these squares solutions. The less comes up a lot in doing multivariate normal calculations and dealing with covariance and precision matrices for multivariate normal distributions. And the IU decomposition comes up in a variety of contexts, including doing principal components analysis and other variants and those sorts of factorization. So what I'm doing here is just trying to, I don't know that I'm going to say all of this here, but what I want to do is just sort of try and lay out systematically what are the different properties of these different decompositions. So I've tried to indicate here what the dimensionality of the different matrices are. And I've tried to indicate here, sort of what are the restrictions in terms of when are these different factorizations applicable. And then what I've tried to write out here is what are the properties of the resulting factors, the resulting matrices that can be used to reconstruct the original matrix. So for a number of these, basically SVD is sort of a generalization of the eigen decomposition, and so we have U and V being orthogonal, just like in the case where we have A being square and symmetric. We have gamma and its square transpose, and gamma is orthogonal. Then a number of these other ones are basically now trying to come up with triangular factors in some way, basically into either orthogonal or triangular matrices, because both orthogonal matrices and triangular matrices tend to be easy to work with. So orthogonal matrices, the determiner is either 1 or -1. Triangular matrices are easy to invert and easy to do, which we're going to see in a second, easy to find a system of equations when you have a triangular matrix as the matrix involved in the system of equations. I think that's all I'm going to say about this for now. Any questions about that? Okay. So let's go back to this problem here. For the basic plan of attack here is going to be, we're going to first start and say, what if we have a triangular system? We'll see that we can solve that system quite easily. And then we're going to say, okay, often in general, we don't have a triangular system. So the answer is we're going to do one of these factorizations to produce a triangular system, and then we're going to work with a triangular system that we've achieved. So that's sort of the general plan of attack, both for today and more generally for dealing with these kinds of problems. Okay, the other thing I want to mention is the sort of two things that we're going to focus on are, A, what's the order of computation for the calculations that we're doing? So basically, is it order of n calculations for an n by n matrix? Is it order of n squared, order of n cubed? How does the size of the amount of calculation grow with the size of the matrix? And that's going to tell us what we could actually do on a computer in practical time. And the other is, what are the tricks that we use to make sure that we can get numerically reliable answers on a computer, given the imprecision with which we can represent numbers on a computer? Okay, so suppose we have an upper triangular system like this, and I'm trying to find the x's. So as you would guess, if we sat down and thought about this for a brief period of time, you'd be like, okay, well, this is a pretty easy system to solve. What do we do? Well, we're going to start from the bottom. We're going to go up. So this is actually going to be called the back solve operation. And the reason it's called a back is because we're starting from the bottom up. So, okay, well, in order to find xn, I can just take xn is equal to bn divided by ann. And once I know what xn is, well, now if I look at multiplying this column by this row, well, there's only one unknown at that point. I just don't know what xn minus 1 is. So I can solve for xn minus 1. So I'm probably going to mess up the indices at some point here. But we end up with xn minus 1 equals bn minus 1 minus an minus 1 comma n x n over a n minus 1 n minus 1. And we can proceed in similar fashion as we find the x's here. As we go upwards, we're still going to have a single unknown in a single equation. That's going to be easy to solve. So the general solution is going to be xk equals uk minus the sum j equals k plus 1 to n xj a k j over a k. Okay, so hopefully I got the indices right. Any questions about this? Okay. So this is easy to do, and then we can ask how many computations do we actually have to do if we're doing this calculation. So we're basically only going to count multiplications and divisions, and the reason being sort of twofold reasons. One is that it takes more time to do a multiplication and division on a computer. The other is that for almost all of these problems, there's either an addition or subtraction that goes along with every multiplication or division. So if we count the multiplications and divisions, that basically also means we're counting the additions and subtractions. So I think depending on sort of what source you look at, in some cases when people are calculating these things, they'll count both the multiplications, divisions, and the additions, subtractions. In other cases, they may just count the multiplications and divisions. It doesn't really matter in general, and I think we'll just focus on counting the multiplications and the divisions. Okay, so take 20 seconds or so and think about how would you go about calculating how many calculations I have to do in order to come up with my answer to find x. And you might start by saying, well, without even doing any calculations, can I just make a guess as to, sort of an educated guess as to how many calculations I'm going to have to do? Okay, so one way to think about this is how many for loops if I wrote this as for loops on a computer, how many for loops would I have? How many nested for loops do I need?
N for loops?
Well, you're going to iterate over n, but you don't actually need n different nested loops, right? 2? Okay, so what are the loops I need to do? Well, I'm working my way up from the bottom, so there are n rows that I need to do, so there's a loop there. And then for every row where I do a calculation, I'm basically working my way across the entries when I do that summation there. So that's the second loop. Okay, so we can say just based on that, without doing anything else, that however many nested loops is basically going to be, that's the order of the n. So in this case, it would be order of n squared. The fact that we're dealing with a triangular piece says, well, you know what, we're not actually doing as many as n squared because I'm not actually doing calculations with the lower triangle. So we might guess even without doing anything, it's going to be n squared over 2. And if we actually write it out, we'll see that's the case. So what do I do here? Well, I'm going to do one division there. Okay. What am I going to do here? Well, I have to do one multiplication and one division. So that's 2 calculations. The next time I'm going to have 2 of these terms that I'm subtracting off, so I'm going to have 2 multiplications, 1 division, so 3 calculations. And I'll just work my way up. I'll see how this is a pretty obvious pattern, and I'm going to get to n when I get to the top. Okay. So if I need to add that up, you may or may not remember the formula that x from, let's say, x from 1 to n of x is n times, I'm not forgetting, is it n minus 1 or n plus plus 1? N plus 1, yeah. N plus 1 over 2. So we should, in this case, so this is just this, so we're going to have n times n plus 1 over 2. So if we look at just the n squared term, that's n squared over 2. And then we can just say, well, the rest of it is just going to be order of n calculations. And it's not, maybe we probably don't really need to pay attention to the constant there. So that indeed works out to what we said, just sort of from an educated intuition would tell us this should be. Where am I seem to have lost some of my sheets here. Okay. Any questions about that? Okay, so if we had a lower triangular matrix, this would basically be the same sort of calculations working from the top down. We would have figured out that it's exactly the same amount of calculation as well. Okay, so either one of those is. And that would be called the forward solve because we're sort of going in the forward direction. Okay, so if I wanted to actually do this in R, what it would look like is, for the moment, I'm just using, with the cross product there, I'm just creating a positive definite x so that I am sure that I have something that I can actually invert. And in this case, I'm going to do a Cholesky decomposition just to get my upper and lower triangular matrices. But I sort of ignore the fact of where the U and the L came from, because that's not really the point of this example here. The main thing I want to show is what the syntax is for solving a system where you have an upper triangular matrix. That's just back solve U and then the result of the vector B. And then if I had a lower triangular L, then I would do forward solve with that matrix and the vector. And if we actually use all that equal, we should check whether two vectors are the same up to numerical precision. What I would see if I did this compared to actually explicitly inverting the matrix, which is what solve does, and then matrix multiplying by the vector B, I would see that doing it with the back solve is equivalent to doing it this way in terms of the numerical result I get, and similarly here. But as we're going to see, if I do it via first doing a factorization and then doing either a back solve or a forward solve, I'm actually going to save quite a bit of computation relative to actually explicitly inverting the matrix and then doing a matrix multiply. And it also turns out to be the case that you might imagine if I have the matrix U actually stored, and what I want to calculate is U transpose inverse B, I don't actually need to do transpose of U and then forward solve. What I can do is say, use the back solve call with U, but say transpose equals true, and that avoids the step of actually explicitly doing the transpose. And you can imagine the reason that this is possible is if you think about what the C code would be underlying all this. This is basically a set of a couple for loops, and it has to go pick out pieces of the matrix. Well, there's no reason to actually do the transpose first if you can just set up the for loop so you just pick out the right pieces of the matrix without actually doing the transpose. So that's a sort of simple example of a lot of these cases. If you were to look into the documentation for LAPACK, the linear algebra package that underlies most numerical computing, you would see there are lots of different variations on calculations depending on whether this matrix is transposed and this one isn't, or is this one upper triangular, or is this one stored as a lower triangular, and all those things. And it basically amounts to being smart about doing the for loops and going and grabbing the pieces that you need. Okay, so I put this in bold. There are three reasons to follow the instructions here in this in here, which is don't actually explicitly calculate the inverse. First of all, you're going to save time if you do it. Second of all, if you are inverting matrices after you take this class and somebody sees you and asks who taught you, I will be embarrassed if you are actually explicitly inverting the matrix. And I had a third reason, but now I'm forgetting what the third reason is. Faster, don't embarrass me. Anyway, okay, those two seem like they're reason enough. I think the only time that I can think of that you would want to explicitly invert a matrix, there are probably other times, is if you have an information matrix for an asymptotic covariance and you need to actually invert it to get the explicit asymptotic covariance matrix. In that case, you actually need to do the inverse. Okay, so we said, okay, we can handle triangular systems. How do we get to a triangular system? Well, one of the ways is to do an LU decomposition, which is one of the decompositions I have over there. The idea is to decompose a square matrix A into a lower triangular matrix times an upper triangular matrix. And then if we need to do A inverse times B, well, that's just going to be a lower triangular solution and an upper triangular solution combined together. Okay, so we're going to walk through this in some detail here, and the idea is I want to sort of walk through a few of these examples in detail just so you get the flavor of how these things work. I'll have you do some of that, a bit more of this on the problem set in terms of the Cholesky decomposition, and then when we get to the SVD and the eigendecomposition and to some extent the QR, I'm going to sort of gloss over some of the details but give you a flavor of what goes on behind the scenes. So that's the plan. Okay, so the LU decomposition is basically a factorization that amounts to doing Gaussian elimination, which you guys should have seen at some point in your student careers. At this point, I've sort of forgotten when that would have been. Okay, so we're trying to solve this system of equations. We can write it out as each of the rows of A multiplied by a vector x is equal to the result bi in the B column. And if I actually write that out as equations, that's equivalent to, I guess I could have written these as capital A's. That's equivalent to this set of equations. Okay. So the idea of Gaussian elimination is I'm going to do a series of operations to this set of equations such that I zero out the A's in the lower triangle here. That's going to give me my upper triangular matrix. The process of doing that zeroing out, as we're going to see, can actually be written as a lower triangular matrix. And as a result, we can write A as being L times U, lower triangular times upper triangular. Okay, so you guys should remember, I guess from, I don't know, high school or something, when you're talking about solving systems of equations, that we can basically take linear combinations of equations, and the result is going to preserve the solution. It's going to preserve the answer x. So the trick is we're going to work our way down, and we're going to zero out this guy, and we're going to zero out this guy, this guy, this guy. Then we're going to zero out the guy here, and on downwards, and the result is we're going to zero them all out. Okay, so the recipe for zeroing out this guy is that we're going to take the appropriate linear combination to result in that being 0. So we want to take some C1 times A1 dot transpose x plus some C2 times A2 dot transpose x. The result is we're going to have, and we're going to then have C1 B1 plus C2 B2. We're going to call that B2 the new B2. Okay, so if we let C1 be equal to minus A21 over A11, and if we let C2 be equal to 1, if you just work through the arithmetic, you'll see that that will indeed zero out A21. Okay, so I'm going to do this. I'm going to replace the second equation with the result of doing this, and as a result, I'm going to have a new series. So I'm going to be taking this, and I'm now going to have my original first equation, and a new second equation that was cleverly chosen, minus A21 over A11 times A12 plus A22x2 equals B2, 1. How do I want to talk about this? Okay, so we've now zeroed out this guy. Okay, so that's our first set of operations. Now I need to zero out A31 and get a 0 here. And I'm basically going to do the same thing, except I'm going to have minus A31 over A11, and I'm going to have, again, a 1 here. So I'm going to now get a new set of C's. I'm going to replace this third equation with the result of using these new C's in the same way I use these C's. And I think I'm now going to I'm going to call this A221.
and A2N1, A2N1. Wait, what did I do here? This is not X1. And so now I'm going to get A321, X2, A3N, 1, XN, B3, 1. Okay, so I'm going to proceed in similar fashion until I've zeroed out the first column. Okay. Okay. So, what do I want to do first here? Okay, so then the next thing I'll need to do is, okay, now if I look at this matrix, what do I want to do? I want to sort of take this piece of it, this piece of it here is now fully occupied with non-zeros. I want to now take that matrix and basically, I guess I want to think about it as this matrix here, sorry. Everything except for the first row and the first column. I now want to take that matrix and repeat the set of operations that I just did, but now this is n minus 1 by an n minus 1 matrix. I'm going to zero out this A22, I'm going to zero out the A321. I'm going to zero that out, and then I'm going to zero out all of these guys. I'm going to then reduce my matrix down to an n by n minus 2 by n minus 2 matrix, zero out the appropriate elements of the first column there, and proceed on down until I've achieved a full upper triangular matrix. So that's the plan of attack. You could write out the arithmetic calculations in terms of notation if you wanted to. It's straightforward, but there's all this bookkeeping involved of what are the indices, what are the sort of new superscripts to indicate what stage of the calculations I'm in the middle of. So I don't think we need to sort of walk through the arithmetic, but I think you sort of hopefully are getting the feel of what's involved here. Any questions at this point? Okay, so let's now focus, as I said, I want to focus in these things mainly on two things. One, how many calculations do we have to do? And two, what are the numerical issues that can arise and what are the solutions that can help us improve the numerical qualities of the calculation? So in this case, we can think about, for each of these guys, how many calculations am I going to do? Well, okay, to zero out this guy, let's see how many calculations I had to do. I had to do this division, A21 over A11. So that's one calculation. And then I had to multiply it by this number. And if we looked at the next one of these new A's over here, I'd see I'd have to do yet another one of these multiplications. So I've got one division, and then there are going to be n minus 1 terms here, n columns, n minus 1 of them. So there are going to be n minus 1 of these multiplications. So I've got n calculations involved in zeroing out this guy. Okay. How many of those, now if I want to zero out all of these, well, there are n minus 1 rows of this. All of these calculations in here essentially are equivalent in terms of how many calculations I have to do. So this is going to be n times n minus 1 calculations to deal with this column. Okay. If you now sort of think about, well, what's going to happen when I get down to this matrix? Well, this is equivalent, except it's now an n minus 1 by n minus 1 matrix instead of n by n matrix. So instead, I'm going to have n minus 1 times n minus 2 calculations to deal with this column. And if I proceed in that fashion, I'd want to check to make sure that everything's following through. But what I should see is, okay, there are n of these columns, although once I get down to here, I don't need to do anything with the last column. So what I should end up with, and I'll just check my notes to make sure I'm getting this right, is I should end up with 2 times 1 as when I zero out the n by n minus 1th element down here. Okay. All right, any questions? Okay, so if I go ahead and add these guys up, well, what is this? This is just the sum of I from 1 to n minus 1, I plus 1 times I. That's going to be the sum I from 1 to n minus 1 of I squared plus the sum I from 1 to n minus 1 of I itself. Sort of running out of room here. I had a graduate instructor for my master's level probability class and also for time series who was very detailed about it and very precise about where he put everything on the board. And so he'd sort of have this all nicely laid out, and then he'd run out of room, and he'd be sort of very precisely making these little boxes and saying, I'm going to steal some space, and then he would write things out in a very nice fashion there. As you guys can see, I'm nowhere near that organized, so, but hopefully it's not too bad. Okay, so what's going on here? Okay, so we had our formula over here. There's the other formula that you presumably would have seen at the same time as you saw that first one, which is what if I'm adding up x squared, and that is n times n plus 1 times 2n plus 1 over 6. So if we apply those two guys to these two, but realize that our summation only goes up to n minus 1, we're going to get n minus 1 times n times 2n minus 1 over 6 plus n minus 1 times n over 2. You continue with the algebra here, you will arrive at n cubed over 3 plus something, some constant times n. It turns out the n squareds in this particular one cancel out. So this is an n cubed calculation, order of n cubed. And the constant in this case is 1/3. We're going to pay attention to this because as you will see on the problem set, what you should end up with is the answer to the Cholesky decomposition. You should get n cubed over 6 instead of n cubed over 3. That sort of makes sense that it's n cubed over 6 for the Cholesky, because if you look at the Cholesky decomposition, for the LU, we're working with A, n by n, and A is not symmetric, so we have to work with n squared different unique elements of A. And we end up with both an L and a U, which are distinct. If we do the Cholesky, A has to be symmetric, we're only working with half as many elements. We only have a single U to calculate, we only need to calculate the upper triangle, and then this guy is just the transpose of that. So it's half, basically, that's sort of the intuition for why it's half as many calculations to do the Cholesky decomposition as to deal with the LU decomposition. Okay, what else do I want to say about this? Yeah?
So what's the order of calculation to get A inverse directly?
Okay, so to do A inverse directly, you basically do an LU decomposition, and then you basically you can do back solves and forward solves into the identity matrix to get the result. And what you would see is that, off the top of my head, I think I gave this actually as a problem last year in the problem set. I think the answer was that it's 5n cubed over 6. So it's actually something like, not quite 3, but almost 3 times as much calculation as just getting the LU. And as we've seen, if you do a back solve and a forward solve, we're working with order of n squared calculations. So you can imagine if we do the LU, and then we do a back solve and a forward solve to do, so we're going to do L times U times B, we're trying to do LU inverse, so that's going to be L inverse and U inverse, so it's going to be a back solve and a forward solve. So there are two times n squared calculations going on there, plus the order of n cubed over 3 calculation to do the LU decomposition to start with. This is going to dominate the calculation in doing A inverse B.
All this kind of numerical trick is trying to tune the factor in front of n cubed, not really reducing the n cubed problem.
Yeah, right. There's not really, right. I think for the most part, there's not a way to get it down to be lower than n cubed. That's sort of a necessary ingredient of these calculations. But the tricks are to try and get this constant to be smaller, or, and what is happening a lot in the last 5 or 8 years, is trying to figure out how to parallelize these algorithms such that you can distribute the computations across multiple cores and do them in an efficient fashion while reducing the amount of communication that you have to do. I guess the other thing I'll say here is even before we started with this and determined this was n cubed, if we think about what this is a this is a loop over the rows. For each of the looping over the rows, it's a loop over getting these coefficients, so 2 nested loops. And then we're looping over the columns as well, so 3 nested loops, order n cubed. Okay, so what else do I want to say about the LU? So we basically, once we've done this, we've gone from A to U, and we now basically have Ux equals B star, I'll call it, because the B vector has been transformed. Right? So now if I want to find X, all I need to do is solve my upper triangular system. We already did that, right? So we know how to do that. And we also know how many calculations it will take. But the other thing that we haven't seen here yet is I promised you I was going to give you a decomposition with an L matrix and a U matrix, and we haven't seen what the L matrix is yet. Okay? And you might be saying, whoa, wait a minute. If I have to find the L matrix, that's going to start adding on to the amount of calculation I have to do. So it turns out that's actually not really the case. And it's not hard to see if you sort of work through the details. We won't work through all of them. But what basically happens is the following. I can write this system of transformations I've done with the multiplying by the A21 and the A over A11 and the A31 over A11 and the A31 over A11 to get to here, and et cetera, as the following series of operations. I can write it down as a lower triangular matrix Ln minus 1, Ln minus 2, L1 times A produces my U. And if we look at what the elements, each of these is lower triangular. If we look at what the elements of those matrices are, L1 is 1 on the diagonals, minus A21 over A11, minus A31 over A11, so on and so forth, and zeros here. Sorry, I'm sort of getting things out of alignment here. These are all zeros, these are all zeros, these are all zeros. L2 looks similar. L2 is 1 zeros, 0, 1, minus A, 3, 2, 1, the transformed guy there, A, 2, 2, 1, this is A, 4, 2, 1, A, 2, 2, so on and so forth. Still 1s on the diagonal, and now zeros here, and zeros above the diagonal. Okay. And it continues in similar fashion to that. You might still be saying, well, wait a minute. If I want to now produce my L matrix, well, L is going to be the inverse of this whole product of things. So Ln minus 1 down to L1 inverse. Wait a minute here. You just told me that doing the explicit inverse is a really computationally intensive task. Not only that, I have to do a whole bunch of matrix multiplications, which you also know are n cubed. So this is looking horrible, right? But, well, let's step back a second and say, well, wait a minute. These are very structured matrices. First of all, they're very sparse. Second of all, they're all lower triangular, and they all have this particular structure. So we can actually analytically work out what the L matrix is as the inverse of doing these matrices. And if we work it out analytically, it turns out that the L matrix does not require actually any more computation. Let me try and save that. So it turns out the L matrix is of the form 1, A21 over A11, A31 over A11, and so forth, A321 over A221, so forth, and on down. There's a 1 here, there's a 1 here, and this is A, n minus 2, n minus 1, n minus 2 superscript, A, n minus 1, n minus 1, n minus 2 superscript. And if we write out, we can explicitly write out what U is and U is just A11, A12. This is A221, A332. Okay, well, so subscripts, dealing with the subscripts is just sort of a pain in terms of the bookkeeping. But the key thing to see here is all of these pieces are things that I actually would have computed as I was going through this process. So I get the whole decomposition for free as a result of doing the Gaussian elimination. Yeah, so I don't, sort of the details of making sure that we've got all the subscripting right, I don't think is all that critical. The main thing I want you to take away from this is that you could, once you've sort of seen this, and if you then sort of figure out what do the individual L matrices have to look like, then this is the basic form of what things look like. Okay, so questions or comments about that? Okay, so the last thing I want to say about, so I guess I'll say this. If you actually looked at what the solve function is doing in R, what solve in R will do is you can use solve on just a matrix, and that will actually explicitly do the inverse. That's the thing I would prefer that you not do, or if you do it, that you not tell anybody. You can also do solve A comma B. This is something that I'm perfectly happy for you to do. And what this does is it basically does this LU decomposition and then does the triangular solutions to then do A inverse times B. Not explicitly doing A inverse times B, it's doing the LU and then it's doing the back solves or forward solves to then find what X is equal to. And behind the scenes it uses a LAPACK routine called DGESV. D stands for double precision. This goes back to the days when LAPACK was started when people were still using single precision floating points. So 4 bytes instead of 8 bytes. So there's an SGESV. I forget exactly what the GE stands for. Maybe general equation solution or something. That sort of naming convention for LAPACK is a bit opaque. Okay. And if you search on Google and look to see, well, what is this DGESV business doing? Well, it's just doing an LU decomposition with something called partial pivoting and row exchanges. Okay, so that sort of leads into the next question, which is what about numerical precision and what could go wrong if we follow this recipe that we just worked out in some detail here? Okay, so basically, let's see an example of what could go wrong here. So remember our friend C1 is equal to minus A21 over A11. Okay, and more generally, we're going to be doing a division where we have something divided by some AKK at the k minus 1th stage of the algorithm. So let's think about what happens if we do this division numerically. So we're on a computer. We know a couple things. We know A11 cannot be represented precisely. We also know that A11 might be the result of having done some other calculations, and we could have lost some accuracy in doing those calculations. So now let's think about what happens if A11 gets to be quite a small number. Okay? If A11 is a really small number, I'm dividing some number of some order of magnitude by something that's really small. I'm going to get something that could be quite big. And now think about the fact that I can't represent that small number, or I may not have calculated that small number with very much accuracy. I'm going to have some fluctuations in the denominator. If the denominator fluctuates from its true value by a little bit, and it's a small number, I'm going to have huge changes in the resulting value for this after I do the division. Okay, so the result is that I could have these errors in A11 propagate out into big errors in doing the whole set of calculations in the decomposition. I could get wildly inaccurate answers for the problem at hand. Imagine this is the first calculation. This is then going to sort of propagate down to all of the rest of the calculations, or at least some of the rest of the calculations that I'm doing. Okay, so we can see this in an example. So suppose I have this system of equations. 3 zeros. x1 plus x2 equals 1, x1 plus x2 equals 1. Okay, so this is not a hard system of equations to solve. We could give this to a ninth grader, or wherever it is that we learn to do this, and they would go ahead and hopefully happily proceed onwards. The answer is x1 equals 1.0001, x2 equals 0.9999. It goes on beyond this, but that's the answer up to four decimal places. Okay, so if I think about now working through this and doing it on a computer, and what I'm going to do for the moment is imagine that I have a computer that only gives me 3 digits of 3 decimal places of accuracy. So I'm going to sort of falsely.
Solution is not solution of the same equation. 1 plus 3
Sorry, yes, you're right. Well, let me just change that. Okay, that is indeed what I actually have written here. Okay, so that's that. Thank you for doing the whatever the 8th grade solution and realizing I made an error there. Okay, so for the moment, just as for this toy example, I'm going to imagine I have a computer that actually only gives me a few digits of accuracy, and we're going to see what happens if I actually play this out and try and follow the recipe that I've prescribed, that I've said is sort of the recipe that we follow here. Well, what's going to happen? I'm going to transform this equation, the second equation, just like I did here. I'm going to have minus 1 over 0.0001 times 0.0001 x1 plus x2 equals 1 plus 1 times x1 plus x2 equals 2. This is the transformation of the only 2 equations to get my new second equation to give me an upper triangular system. Okay. So the answer, so if I do this, what do I get as my new second equation? This guy becomes minus 9999x2 equals minus 9998. So we're seeing this play out. If this is small, I'm going to start to work with some big numbers. Well, now suppose that that I can't represent this with I can't represent this equation with full accuracy, and I actually I can't represent this last digit accurately. So suppose this actually gets rounded off, and the equation that I actually end up with as my second equation is this. Right? This is basically an approximation of this equation where I lose this digit of accuracy, and so I just end up working with, rounding. Okay, well now if I solve this equation and this equation, those being my new system of equations after the transformation and the idea that I can't represent things, that I only have, say, 3 digits of accuracy, what do I get? Well, I get that x2 equals 1. Wait a minute, what's going on here? Oh, right, okay. So I get that x2 equals 1. If I then now I need to go back up and plug in to solve into the first equation. I get that so now I get x2 is being equals to 1, and because I don't have enough digits of accuracy, the result is that I'm going to get that x1 is being found to be approximately equal to 0. So I get this as my answer to where the true answer is that they're both right around 1. So that's sort of a toy example of sort of trying to illustrate what can happen if you are dividing by a small number here. Okay, so for my toy example, does anybody see what I could do that would solve this problem and avoid this division by a very small number? Okay, so I want to choose to divide by a different number. Well, how could I arrange things here so I do that?
Multiply the first equation by a column.
Okay, so I can think about multiplying by multiplying one of the equations. There's another approach that I could take. Anybody see another possibility? Is that it? Okay, so I could just switch the rows, right? This is a system of equations. There's nothing magical about the fact that I happen to put the first equation first and the second equation second. Let me just switch the two rows. As soon as I do that, instead of dividing by 0.001, I'm going to be dividing by 1. Right? So that's basically going to solve all my problems. If I went through and switched those, and then I played through this idea of what if I have limited digits of precision and I have to do some rounding in the representation, the answer that I would get is I would get x1 equals 1 and x2 equals 1. Well, that's not exact, but it is my best, say, 3-digit approximation to the actual answer. So that's basically the story if you hear the term pivoting associated with the LU decomposition, or sort of more generally, there are sort of similar kinds of steps that you would do. Well, I guess the switching is right here if you were reading along. Basically, what happens is we basically want to choose. Suppose let's see, where was I here? So remember when I zeroed out these guys, what was I doing? Every single one of them had something divided by A11, right? Well, what's the story in the pivot in terms of doing pivoting when I'm trying to zero this out? Well, basically, I scan through all of these elements and I say, which is the maximum element of the A matrix in the first column? If it's not A11, but say it's A61, I'm just going to take the sixth equation, move it up to the first position, and then I'm going to be dividing by that A61 instead of the A11. That's going to stabilize the computation with respect to zeroing out this first column. Similar story as I proceed through. I now have my n-1 by n-1 dimensional matrix. I scan through my new coefficients in the first column of this reduced matrix. I find the maximum one, and I switch that set of equations. Okay? I continue, and I basically reorder the rows as needed. So I can basically write that. I remember in the initial reading of the unit, we talked about permutations as just using that you can write that as a permutation matrix multiplied by the matrix. So I can write out this series of permutations that I would do for the pivoting here, of the row exchanges, as a series of permutation matrices. A series of permutation matrices just gives me one resulting permutation matrix, P, which is the product of those guys. And so basically I can write my system of equations as P times A equals LU. So that's the LU decomposition with the pivoting, with doing the pivoting. Let's see, I'm not sure what else do I want to say here. I guess not much, since I don't really have any time left. Let me just see if there's anything else I have here. Okay, so let's stop there. We'll talk fairly briefly about the Cholesky decomposition next time, and then we'll launch into talking about the QR decomposition and doing regressions. Oh, and for those of you who came in later on, your returned problem sets 3 are up here on the table in alphabetical order by last name.